Okay, my outstanding friends, this is going to be fun. I've been waiting for this forever. Now, I get all the scientific journals every day, and this one here is Science Alert, and they're literally everything I've been talking about is on this page. On this autism, I've been looking into autism deeply. We're talking about the DNA of our ancient ancestors, yes. Talking about the global warming and how the heat dome is moving over the earth and why it does and how the heat interacts. We're talking about how did civilization develop? When did it start? A lot of this they're putting out to cover what they had said in the past about these things, which now have been shown not to be correct. But they're still, you know, trying to figure out some way of hanging on to this. Now they're talking about iron hands in the 15th century changed how we do medicine, whatever that means. The great red spot on Jupiter, I fully understand that, and this is something that's got to be investigated deeply, and I have commented on this over and over. They're saying it might not be as old as we thought. Well, it isn't even what they thought it is, so we got to start from what it really is. It's not a storm. This is viruses. I've been talking deeply about the interaction between enzymes, which are created by bacteria, and viruses, and all the nucleophilic substitution and invasion that happens in your body, and the membrane layers and collagens and so forth, and the different types of collagen. I don't want to get too deep into any one thing, because the one thing I want to comment on right now, we're going to go into the light. And here's the other one. The light is my big one. This was, well, I like all of this stuff, but this, until you understand what light even is, you don't even know what matter is made out of. They don't know what matter is made out of. You can believe it or not. They have no idea what matter is made out of. That's what these huge colliders are all about. They're not just there, I don't know what you think they're there for, but they're there to smash particles into the tiniest bits and pieces they can find, which is elementary particles, which is down in the light realm, which is what I'm going to show you right now, because they say they figured out how heavy a particle of light is. I don't think they know what a particle of light is in the first place. Secondly, let's see what they have for a weight, because I think I do know how much a particle of light weighs. So let's dig into that. But then right down here, they're talking about body organs being in the wrong place in a body. I've been discussing a new, what I call a spurlock. It's a latch on body parts, and this is one right here. I've shown this in a microscope. This is a piece of meat. It's a mud fossil, but they have these latches on them, and that was latched in to another organ or another body part, and that's how body parts stay where they're supposed to be. They're just talking about body parts ending up in the wrong place. This is just phenomenal that these things that I am exposing every day happen to be all right on the same page in one day. It blows my mind. Okay, home of the shocker du jour. How heavy can a particle of light be? Well, scientists just figured it out. Yeah, we got it all figured out now. Well, they don't know what light is to start with. First of all, they don't understand what light actually is. Now listen to this. Photons typically are described as massless particles. That is not true whatsoever. These discrete quantities of energy zip through space time at a constant speed. Not true whatsoever. Unable to accelerate or slow down in a vacuum. Not true whatsoever. There is no vacuum in space. Space is not empty by any means whatsoever, as is stated by Fermi. Whoops, that's the standard model, not successful. The quantum foam, empty space isn't empty. It's saturated with particles like a foam on the head of a root beer, they say. Now also, things weigh less on mountaintops than at sea level. The weight changes because of the decrease in gravitational acceleration due to altitude. Well, what is gravitational acceleration? It's magnetic fields. The further the magnetic field is away, there's less attraction. When it's right up tight, it's tight, and it's heavy. It gets out here, it's not quite so heavy. It gets heavier and heavier and heavier. It's not really perceptible too much. But as you get higher and higher and higher and higher up into the atmosphere, you just start floating because you're not being dragged down by magnetism. All right, this is what they claim an electron weighs. Electrons are negatively charged particles weighing 0 atomic mass units. That's not true. And located in various orbitals of the energy level outside the atomic nucleus. Also not true. The electron actually weighs this much in grams, which could be about correct. They say it's 1,830 times. This means it would take about 1,830 electrons to equal the mass of one proton. Well, how could the atomic mass units of 0, and make 1,830 times 0 is 0. All right, this is that that kind of math where 1 times 1 equals 2. He said, how could you possibly? They're charged particles weigh in 0 atomic mass units. But if you take 1,830 of them, they weigh the same as 1 proton, which is 1 atomic mass unit. This is insanity. So really what you want to do is divide the weight of one of these electrons, which does have a weight. And anyway, just let's cut to the chase. It's 0.0005484, I believe, is the quantity of atomic mass units is 1 electron. So it's 1,823, I calculated out approximately, equals 1 proton. All right, so instead of 1,830, close enough. It's right. It's in this area. I'm not exactly correct. I don't know if exact, but if Millikan was right about the weight of the electron, which is this, then there would be about 1,830 electrons, just like that, in a ball, that make 1 proton. They say that's 1 proton. I say no, that's a proton, and there's 1,830 dipoles. Every one of these is a little magnet, and that's what these are, is dipole magnets. You see them? They're just little magnets. It's the same thing. You take 1,830 of them together, and for some reason, and I'm not exactly sure, it's called resonance frequency. They lock in at 1823, 1830, whatever, right in that area, and they become stable. Now, they could have a few less and still be pretty stable. That's what's called a half-life. They'll be there for a little while, and some more will come over and they'll finally attach. Or they could have too many, and they'll just drift off into space at some point. Somebody will come by and say, oh, I'll take those extra ones, and then there you go. Those are called isotopes. I'm very familiar with this. I'm going to show you exactly what this is all about. And now they're saying they can calculate the weight of an electron. Well, let's just see, because as I said, they don't know what an electron is. Okay, there is no physicist or scientist that would disagree. Light is light. Is laser light? Yes, laser light is light. It's just more confined, and the intensity increases because of how focused it is, basically. And yeah, this is blue. This one here is green. And this one here shoots out a red pulsed laser. And the red has no power, basically. The green has a lot more power, and the blue is just off the charts. And I can show all of the things I'm saying. This is not just guesses. They know that, they realize this, but I can show it. You see this red? It's just being pushed out of the way by the green. The green is like a zillion times more powerful than the red, and the green is nowhere near as powerful as the blue, and here's the blue. The blue comes in, you can't even tell there's 2 dipoles here. And there is 2 dipoles for every photon. But by the time it slows down, and yes, light does slow down, you can see there is 2 dipoles in each one of these. Now we're going to get down to the weight of a photon, or the weight of an electron. How much do they weigh? They say they're massless. Let's look into this deeply, because they just don't understand the particle. Now, I got to warn you, something I'm taking into account is Millikan's oil drop experiment, which said that the mass of an electron, the least weight that he could find change, and it was always basically the same, was this 0.000544845, I believe that's if you really carried it out, of an atomic mass unit. That's, and then if you took 1800, I say about 1823, it could be somewhere, it could be a whole lot of difference, but there's going to be a certain number of these little particles that make up one proton. Right now they say it equates to approximately 1830 electrons equal the mass of one proton. So that, think of 1830 electrons. But now an electron is not what they thought an electron is. An electron is a dipole. An electron is a dipole. And this literally is what an electron is. It has a glowy side and it has the dark matter side. And the dark matter pushes it. And the white matter pulls towards the dark matter. They glue together. They literally call them gluons. Gluons. That's what they call them. And we have found these, and here they are right there. They're glued on together. You see these? This is a photon. And it's made of two of these. All right? And each one of these is a dipole, which means it has a black and a white. All right, so side by side, you're going to have a black and a white and a black and a white in a dipole back-to-back magnetic configuration. And they have a field surrounding them. So when they hit something, they bounce. What the color they bounce back at is dependent upon how fast it started, how bright it was, the texture of what it hit, all of that stuff plays into what the frequency coming back is. And as I showed you before, the green and the red, these are two different frequencies. The green is very powerful coming back, so that it would have had to start out as a powerful particle and come back as a pretty powerful particle, which means it hits something pretty solid, reflective. This is just going to sort of bounce away easily. The red light doesn't give you much of a, well, red light has no impact value. Red is here, you see this here? This is the red end of the spectrum. Very weak, long wavelengths. And this is where we come into weight. Weight is literally, there is no weight for an electron. There is no weight for an electron unless you want to just quantify it at that 0.0005844. But the weight is a product of hitting something. When you hit it, how hard do you hit it? Like if I drop this, that's a lot more weight than if I drop this. All right, so it's all related to, well, boy, I tell you, this gets tricky because it's a magnetic interaction. So the density of oh boy, this gets too confusing. All right, this could get extremely confusing. So I'm going to try to just make it simple. In the red region, there's no energy, there's no push. As you come up into the blue, you get more and more push. Green pushes pretty good. Blue pushes pretty good, or a lot more than the green, and the red just doesn't really push at all. Well, very little. And a full spectrum light, like this kind, pushes a lot. And we can tell these things do have mass. They talk about massless. This is really unbelievable. These are the people that are running science. Watch this. This is a Crookes radiometer. And they've always been puzzled why you point it at the black and it pushes it away. And you point it at the white and it literally pulls it into the light. Watch this. I'm going to point it at the black. Can you see that? Maybe if I turn this light off. All right, that should show better. Well, anyway, I'm going to put, these are the black veins. They're on the other side of the white. Watch this. Whoops. Ah, run for your life. Everybody okay? Wow, why is this doing this? All right, this is a Crookes radiometer. It's got very little gas inside of it, and it's got these black and white veins. You have the white on this side and the black on the other side of all of them. Now, if I shine this full spectrum light here onto the black, it will push the black and it'll start spinning this way. If I shine it on the light, it will pull the white. If I shine it on the white, it will actually pull the white into the white. Nobody in history has been able to figure this out. I know how it works, and I know why it works. And it's the why is what the thing is. Now watch, I'm going to point it at the black. You see what happens? Boom, it takes off. Now I'm going to point it at the white. You see it? Look, it keeps pulling. Look how hard it pulls to the white. All right, now if that stops, I'm going to let it stop. Hold on. All right, this is fun. I like these experiments. Now, what we're going to be working with is light in the different colors of the spectrum. I've got a red, green, and a blue laser. And I have a full spectrum light. And I have a Crookes radiometer here. Now, what is the difference between the spectrum? They're the length of the waves. The length of the waves literally gives weight to the particle. Think of it for a second now. Down here, these waves, the particles don't have much weight at all. Almost no weight whatsoever. When you get out here and they get crunched up and crunched up and crunched up, they start to have a lot of weight. So there is no real weight to the particle. It's how crunched together it is. Although the particle itself, you could give it an arbitrary weight, and we will. But the weight, if you really think about weight, what weight is the impact. All right, this hand weighs a pound, let's say. But when I smack that screen hard, it may weigh 10 pounds. All right, it would be like just dropping a 10-pound ball on there. So what is weight? What really is weight? Weight is the value of what it impacts with, to me. But if you want to assign an arbitrary weight to a particle, which is what we're going to do, and we're going to say that particle can weigh this much, or this much, yes, but it is this particle. So it's a little hard to understand the concept, but I think I can bring it into focus. Now, speaking of that, we're going to talk about the Crookes radiometer. Get ready. This is going to be fun. Get the kids if you want, because they're going to love this kind of stuff. All right, I don't want to confuse you here. When I said wave before, everybody thinks of something just going like that, up and down, up and down. It's not. It's really spinning in a circle like this. You see this? This is what light looks like when it comes through the Venturi. It's spinning this way and it's spinning that way. And you see these exact perfect lines here? This is in the back after coming through the Venturi. It portrays that on this was a Nike box. You see it? These are not top-end experiments, but they certainly work. Now, this is a drill. You see that? That is a drill bit. You go to any machinist, you say, what do you see? I see a drill bit. Yes, you do. Now, what does that mean? The light is spinning this way. Well, what does that mean? It's spinning, so it's just like it's spinning on this. From the side, it looks like a wave. And that looks like a real tight wave, which would be the blue region. That would be the green, and this would be the red. It's as simple as that. It spins. All right, and whoops, you see them? They're separated, and you can see the particle is spinning to the right, which means it drifts to the left. This one shot picks up that photon as it moves that distance. You can see it's spreading out here, and you can see that there is two dipoles. Here you can't really tell. So we know we can slow them down. We know we can speed them up. We know we can divide them. But nobody else can. We can divide these. These were attached, as you see them right here. There's no question about it. And these are the tiniest particles they can find. Light is the tiniest particles that exist. Nobody's denying any of these things. And then we accelerate it. Nobody can deny that. We split them up. Nobody can deny that. And this is what Fermilab and CERN call these neutrinos, and we found them, and these are creating electron showers, which are the cat's meow, millions, trillions of electron volts you can get from those. All right, this is a perfect example right here. I am going to use this. It's going to be red laser. And then I've got this one here. I think it's the green. I got a green and a blue. Yeah, this is the green. And so this is what we have here, the green and the red. Now, the red will not move that Crookes radiometer. You see this? Nothing happens. I go to the black. Nothing happens. Go way back here, nothing happens. I get way up close, nothing happens. I go to the white, nothing happens. You see how bright it is? Boom. No, there's still nothing. All right, so we know this doesn't work. Red has no energy to speak of. Now we're going to go with the green. All right, so here's the green. You see it? Now watch what happens. Green against the black. There it goes. Come on, baby. Come on, baby. Come on. Get it. Come on. Come on. You can do it. You can do it. You can do it. Boom. Now, what happens when I go against the white? So it doesn't move it. So this is obviously some mass. Something is moving it. It's not moving for nothing. It's, oh, that's a magnetic field. Well, so what? How did the magnetic field get there? Because of a particle. Now, I'm going to go against the white. Now, will it come towards the green? It might. Come on, baby. All right, it just the green doesn't have enough to bring it towards the light. Now, here's the blue. You see the blue move it pretty quick? I'm just shining on the black. You can hardly see it, but it's there. Now, we got to let that stop. All right, so you saw the red had no energy to speak of, and you can see it doesn't have any energy. You see it in the shot here? The red just gets out of the way, and the green takes over and reconcusses out here. So we know the green has more energy, more push. It pushed that out of the way. It's pushing forward through the particles in the air. It's pushing. So there's something pushing through there. And I can show you that pusher. Now that's the green. Then we had the blue here, and we know that the blue can make it go this way. Can the blue make the white come towards it? No, it pushes it away. What the hell is going on? That was interesting. Now, we know the blue can push it. Can the blue pull it? That's the key. No, it pushes it. That's pushing. Now it appears not to be doing anything. All right, so I'm going to go with it won't pull, but it will push. You see, we're pushing now against the black. It'll push it, but it won't pull like the white will. The white light will push if it's going against the black, and it will pull if it's going against the white. So why is that? The white light is all these frequencies together. I understand why. And you could never understand it until you understand the reason behind it is the glass. Nobody's ever taken that into consideration. It's the glass. All right, we're going to get into all these pictures in a minute, and I'm going to explain to you what they all mean. And these are from Fermilab, and mostly all the rest are from us. That's Fermilab too. And I will show you what their claims are about particles and space is not empty. And they say that. No, it's not empty. It's obviously not empty. Okay, let's just start off with this. These are the particles that they find at CERN and Fermilab. That one never changes. This one gets big and small. We found the exact same particles. And glued together, they create a photon. That's what a photon is. And this is colorized. And it shows the energy levels surrounding, exactly identical to what they say at Fermilab and CERN. So this is a photon of light, light being one of the elementary particles. There is what they found at Fermilab. And it acts exactly as the particles that we found. This one never changes size. That one can puff up and get small. And that has all the energy, that has all the mass. Now, they also at Fermilab claimed this standard model is the most successful theory ever. Well, there's two tiny particles. This is the black one and the white one that I just showed you a second ago. That's all there is. All the rest is just manifestations of these two. Back to back, these will glue together and they form what is a gluon, but they can be separated as I showed you in our work. Two gluons make a photon. After that, nothing gets stable until you hit, I say about 1823, 1830, whatever, somewhere around there. And at that point, it's just becomes stable and it's a hydrogen. And then from there, they just get bigger and bigger and bigger. But 1830 makes one proton. So by the time you hit helium, you've got 2 protons, 2 neutrons. So you got like 7,000 something. And then they go up to enormous numbers up here. But that is what's the beauty of this. It accounts for all the isotopes and half-lives and the ability for life to exist. Life can't make it with these particles. It can't happen. And enzymes break these things down and take little pieces of them and break them down into half-lives within a quarter of a second, and they change all that to make them 2 of these and 6 of these and 4 of those and 9 of those out of a big chunk. That's what enzymes do. And in the middle of every atom is the dark matter. We never see it because it's way down inside. All right? And this is my model. And of course they also say here, quantum foam, empty space isn't empty. It says the foam on the head of a root beer is a complicated environment, bubbles appearing and disappearing, a dizzying display of charge. Empty space experiences similar activity with subatomic particles, which are these little bits and pieces, winking in and out of existence. These particles are real and have a measurable impact on our universe. Absolutely, they're particles of light. Let me show you what particles they are. And these are the particles of light. Now the beauty of this is we can see them because we're not smashing huge things like this and digging through the debris. We're using these. So we can actually just visualize them. We don't have to visualize them and try to decide what's in that mess that they smashed to bits. These are the particles they're looking for, and they found them, but they found them in a pile of debris. And this is what they do. They take big things like this, which are nothing more than balls like that of dipoles. They smash them together and all those dipoles go flying, and some of them end up going into chunks like that, which will kill you, and some of them go into these little bits, and some of them end up going into the photons, which we started with. This is what we start with. All right, so they're creating just a big ball of mess and digging through it. We're actually using the particles of light. So this is actually light from this exact pulsed red laser. Light is light. Well, what happened? In the darkness, you can see that all the other fields took on this little pulse of light as this thing is forcing its way through. And there's a particle in here. Normally you wouldn't see that particle. When I shine this through the air, you don't see anything until it hits something. All right, the air does not normally do this. All right, but it's being accelerated now. And here's the full acceleration. It's pulling itself literally out of the wave, the actual particle. So what does that mean? We're not starting with this. We're down here. And it's coming through here, and all of a sudden it says, wow, there's a restriction up here. We got to force ourselves through here. And it takes off. And here, the black part says, that's too small for me. I can't get through. Well, get out of the way. I'm going through. And the white goes through. That's fission, and back together they come as fusion. That's what it is. In the middle, you have electron showers. All of this, you can look up these terms. They're very, very, very meaningful. Now, I showed you that particle beam. Well, that is the particle. And here it is, close up and personal. Now, the red is so slow that we can see them separated out nicely. You can't do this with the green or the blue. You can do it a little bit with the green, but not like this. I'll show you the green in a second. These are neutrinos. And what is a neutrino? A neutrino is basically like a light particle, but it's only in the phases of moving through the air, so it doesn't have the full photon effect. So it's like they're particles gaining energy. And what does it mean to gain energy? You gain more and more and more energy as you get closer and closer and closer to the target, because your fields are starting to interact. Now, why are these looking like photons way out here? They're fields because the target's way over here. Well, the reason is because it's bouncing back. You see this white wave? That's bouncing back. This thing thinks it hit a wall. It thinks I got to turn into a photon now because I just hit a wall. Well, it didn't hit a wall. It hit a reverse field. And this one here is the same thing. He says, well, I'm hitting a wall too. Only here. You don't see them hitting walls up here or down here. They are starting to gain energy because they're being bashed back at. But back here, you don't even see them. They are here. These particles were back here. Never going to be seen unless they are gaining energy, becoming neutrinos. They're gaining energy, and they say they're turning different flavors, which means they're just getting more and more and more and more energy as they back up against this. You see how they look like an Oreo cookie here, and then they go sideways, and then they do this kind of stuff over here. But the photon is the one that's dead in the center. That's the one that changes the whole into a photon. All right, so this is what they say is massless. It's not massless. That's what we were pointing at the Crookes radiometer, making it spin. And the reason there's the reason for the white being attracted back to the light. Watch. I think I showed you this, but I'm going to do it again. All right, I'm going to hit just the white, and the white will come back to the light. Why won't the light push it? It's going to come back at the light. Watch this. You see that? It comes back. Nobody can account for that. There is no accounting for that. Why would this not push it that way? Why is it attracted to the light? It's like a moth to a flame. All right, the only thing that explains this is dipole electron flood theory. There's no other explanations. My explanation is that this is what a proton looks like. It's not like this with a couple of quarks and so forth. You can smash it into all kinds of little debris. It's like this. But in the center is the dark matter. The black thing is it's dead in the center, so we never have seen it. All we ever see is stuff that bounces back at us. It's in everything. The dark matter is in everything. It's even in light. Light contains dark matter, and I just showed you that. All right, that's dark matter. Those two little black dots. They're muons, they're dark matter. And when you get them in a ball, the dark matter migrates to the center because it doesn't care about being on top of each other. Couldn't care less. It doesn't attract, it doesn't repel. The only thing it does is with the white, wants desperately to be attached to that black. For whatever reason, I don't know. That's the dipole nature. So the white will go through anything to get to that black. That's why it'll go right through you to get to ground. The Earth is saturated with dark particles. Saturated. That's why static, right to ground. Lightning, right to ground. Electricity, right to ground. Doesn't care what's between there. You could be standing there holding a piece of metal. It will go right through you, right through the metal, right through your body, all the water and everything, into the ground. It desperately, these white particles want nothing more desperate to be attached to the black. And you can see it when they come out of the Venturi. You see it right here? They come here and they turn into the white particle. Here is just strictly white, 100% white here. No black whatsoever. And then here they come back in with a vengeance to grab back into the white. That's what electricity is all about, is that white seeking ground, which is the black. Let me just finish up with this real quick. This is what a proton looks like. I'm literally 100% sure of that. I had another model here, this with layering, but I'm almost certain that's not true. I believe this is true. And the first layer is tight, tight, tight to the nucleus, which is the black ball, dark matter. Then the next one is tight against the first layer, and then that one's tight against those, but they're still repelled. So there is distances between the black and the green and the green and the red. There'll be a little bit of a field separation there. Here, they're just locked tight as a drum. That's the strong nuclear force right there. Now, if you come down here, that's the only two particles that exist, these two, the black and the white. Nothing other. And it's a muon neutrino, electron neutrino. This is the standard model. Well, just the differences. We have a gluon, and for them, an electron is just nothing but a negative, and all the stuff in the nucleus is positive or neutral. But neutrons are nothing more than the same as in a proton, only one additional electron, which makes it neutral. Protons are uneven numbers. That means they have a charge. They want to be even. All right, if it's 1823, it wants to be 1824, and it can live with 1822 by sharing one of its electrons with one of its partners. All right, that's what bonding is all about. It's not hard, it's simple. It really is. That's what the photon is. I showed you those. Now there's differences in science, space, redshift, all that stuff changes. The distance with things in space, totally off the charts, not correct. And all of that I can prove once again. No guesses here whatsoever. Light slows down, light speeds up. All right, there it is speeding up. If you can't tell that's speeding up, and I don't care if it's in a vacuum or not a vacuum, this is more unaccepted because it's not even in a vacuum. We're speeding up in a medium. That's beyond speeding up in a vacuum. All right, in a vacuum, if nothing ever touched it and it just kept going, yeah, I would say that's possible. Light wouldn't slow down. But space is, first of all, not a vacuum. It's saturated with these particles of light and dust and everything else and debris. And secondly, the fields are absolutely insane, which I now will show you. All right, this is what they're looking for, is these gravity fields, they call them. That's like a white particle, and that's like a black particle. This is dipoles in space, and they are out there, as I have shown, because this is really what's out in space. These are all dipoles. And these are the magnetic fields. There is, if anybody in their right mind could tell me that particles, these are particles, light is a particle. These particles are not going to be affected by these fields. They're out of their mind. They are literally insane. You can't penetrate these fields without reacting. We know that light slows down in all kinds of different media. And you can slow light down to literally a couple of feet a second now. They got something, I don't know what they did. But what you're doing is you're putting a bouncy field in front of it. It's a bump, 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 bump. And it just slows it way down, as you can see right here. All right? There's no way in the world light can travel at the same speed continuously. It's just nonsense. So literally, we have no idea where we are. All right, when we're talking about the weight of particles, of these dipoles, there's going to be a weight if you just weigh them, but where would you weigh them? If you weigh them on Earth, they're going to weigh 0.000584, whatever it is, atomic mass units, because that's the magnetic attraction of Earth to these dipoles. If you're way up on the top of a mountain, this isn't going to weigh the same as closer to the Earth. The very deep in the valleys, things weigh more. Literally, they weigh more than they do up on the mountains. Absolute fact. There is no question about that. Now, so that, what is weight there? The same object up on a mountain doesn't weigh the same as down in the valley. So what does the weight mean? Weight means how hard is it being pulled to Earth? Well, not everything's in Earth. What if it's in outer space? How much is the weight of that? If it's in not being pulled and pushed and all that by other magnetic fields extremely. It could be out in here. That's okay. How much does it weigh out there? Well, really, you can't say it weighs anything. So the only time you have weight is when you have impact, and everything impacts into the Earth. So everything has weight, which is gravity. And the gravity is the pull of the dark matter to the white matter. And that's no question about that. There's no question whatsoever. The black is pulling the white. And why do I say no question? Because of static electricity. Too much white, it goes right to ground. Lightning, too many ions in the atmosphere, too many electrons, bam, into the ground. Electricity is just forcing the electrons to flow through a wire right to ground. Earth is saturated with dark particles. That's what it is. If you're insulated from ground, you're not going to get electrocuted. All right, it has to go through you to the ground, and it goes through these particles. All right, so what does something weigh? If it's red and it's way out here, like this long distance, like here, boom, 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 it hits something, then bang, no big deal. If it's the green, you see how it is? It's down in this range, bam, it hits something pretty hard. Now if it's the blue, pow, it's like a sledgehammer. So it's the speed of the spin, literally. It's the speed of the spin. And the more spin, the more drifting up into the blue. It's not ununderstood. It's not misunderstood. The more spin, the higher the blue. The less spin, the more the red. And you see how these are all widened out? And it's coming through a lot tighter, the green. This is all verified. This isn't just guesses. All right, and it makes a big difference in chemistry and physics and the whole 9 yards. And it's all dipole electron flood theory. So you better start talking this up, especially if you're going to go into physics or chemistry, any of that stuff, because chemistry's got to change too. Periodic chart has to change. It's not a whole lot. It's just basically how many particles are in an electron, a proton, and in a neutron. You have to multiply those in and say a hydrogen is this ball. It's this big of a ball of those particles. It's not one big hydrogen on one big proton and one tiny, tiny little electron that they say has no mass, but if you had 1,830 of them, they'd make a proton. So much nonsense. They just don't understand what they're doing. So they come up with all these, basically to me, silly theories. But everybody's trying to make a living. But once you understand it, this opens up a big, 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 big doorway into chemistry, into physics, into light, into energy, into the cosmos, and it all ends up going back to our origins and where did all this stuff come from? All right, I love you all. We'll talk later. All right, I don't know how much more obvious this could be. This is from Fermilab. These are Dirac neutrinos. These are Majorana neutrinos, which means they're in the phase of becoming a photon, like this green here. These are the neutrinos for the green. The green is the same particle as the red or the blue. So the same particle. It's just that one's spinning faster than the other. These are the neutrinos coming forward. And of course this is the red. And these are the neutrino values for the red. And here's where the Venturi is, and it hits there, and it's all over. And of course there's the blue rocket ship. You really can't even play around with the blue. You just can't see anything. The red is slow, and now what was I going to show you? Oh yeah, here it is right here. You know that you saw the muon and the electron neutrino attached together, which would be a Dirac neutrino, which is di means two, the two of them together. When they're doing this in heavy water in nuclear experiments, and this is what's called Cherenkov radiation. The muon leaves the electron, and the electron turns into showers in this media, which is a heavy water primarily. We just did it through a venturi. We created our own heavy substance right in front of the venturi by forcing this to collect into that venturi. And at that point, the black, which is the muons, separated from the electron neutrino, which is very, very difficult to do. That's creating electricity. This is electron showers, which is literally raw electricity. You see the black particles? These are all the same size. You would never see them, except they are almost on top of the white. See, some of them here are just barely on the white, and they're obstructing the view of the white. These are pretty much right on top of the white, and so are these. So you can see them easily. Now you see you got a bunch of little black ones right together. They don't care. They'll glob right into a ball together. They don't repel. They don't attract to each other. The white is just voraciously attacks the black. It wants to be attached to that black. Just that's the strong nuclear force. So I think I've presented a pretty good case here.